Hi, everyone. Thank you for joining in today. My name is Owen Marr. I'm going to be talking about the Blue program and how we are increasing student access to space. So I am currently I just graduated, but starting grad school this fall in Space Systems Engineering at the University of Michigan. I'm also the student program manager for the Blue program. And then joining me today is Brandon Dix, who is a rising senior in the aerospace engineering program, and he is the mechanical lead for BX3, which is one of our current payloads. So before we get into Blue, I want to show the background image from that cover slide. This is a photo taken from the ISS. And if you follow my mouse here, you can see this kind of line of horizontal small lines there. And each one of those horizontal lines is one of the SpaceX Starlink satellites. And we thought this was a really cool photo because it kind of dates back and brings back memories of why Blue was originally founded. And so Blue first came about from basically a statement and then a question. And the statement is that space is becoming easier to access. It's becoming more accessible. And this is kind of a truism within the space industry. I think most people agree with this statement. And the question we had was, how can we as students be a part of this? How can we get into space as space is becoming more accessible? And so that's where Blue really stemmed from and where we really got started. So today we're going to kind of talk about what is Blue. I know there's a variety of different people in here from different backgrounds. So we'll do a quick overview of what Blue is and also why we exist. Then we'll talk about some of the payloads we're working on right now and a little bit about where we're going in the future. So we're going to start with kind of what is Blue. So for people not familiar, Blue is biannual launches for undergraduate education. And this acronym kind of explains what we are. So we're doing regular space launches as undergraduate students. And the biannual means that we're doing 2 a year. So roughly every 6 months, we are sending a payload into space. In the middle here, you can see the Blue Origin New Shepard rocket. This is the launch partner we have. So Blue Origin is launching all of our payloads right now. And then to the right of the rocket, you can see our 2 current payloads, BX2 and BX3. We'll talk about those later in the presentation. And then to the left of the rocket, you can see some of our work from BX1 of us in the lab and also designing and stress testing some parts with ANSYS. The first one we did, which was BX1, was actually basically, can we build a tattoo gun that would work in space? So that's just a very brief overview, kind of what Blue stands for. Now we'll kind of jump into some background. So this was founded in 2018 at the request of Dr. Wass, who is the Aero Department Chair. It was actually a budget meeting for SEDS, and he said he was frustrated because he felt like not enough of the undergraduate students were working on space payloads. I think Professor Hollow's 285 class said 55% of all students at the University of Michigan in aerospace are interested in going into the space careers or the space industry. And yet we only have, a fraction of those students actually working on space payloads. And so he said, pitch me an idea for how we could get more students involved in space. And so that's when we came back with the Blue program. He approved that, he funded that, and now we're tasked with regularly launching these payloads into space. And basically this organization is under SEDS as sort of a project team within SEDS, which is really cool. So why do we exist? Well, it's basically to give more students experience developing real space hardware before they graduate. The more students that we can get involved in space payloads as undergrads, that makes them more attractive to potential employers and also just gives them better experience to enter the workforce in whatever way they choose to do that. We also want to demonstrate that the university is a top space university and that we're regularly sending payloads into space. And so by doing one every 6 months, we think that's a good cadence for now. And we're also trying to standardize this process to kind of fulfill our ultimate vision, which is that in the future, any student at the University of Michigan who is interested in space will have the opportunity to work on some sort of space payload before they graduate, which I think is a really cool goal for us. So it is a really cool goal, but it's very hard to accomplish. I know a lot of teams in here have dealt with this sort of stuff before and can attest to the fact that it's not easy to get something into space. So there are a couple ways we're trying to simplify the process and make it easier for students to do this. The first way we're doing this is by choosing a payload system that is manageable and easily repeatable. So for us, that means the 2U mini payload with Blue Origin on New Shepard. This is a very standard size payload. It's pretty well defined by Blue Origin, so we know what we can't do. And it also always has like the same outer case. So all we have to do is adapt the inside to the experiment we're conducting. Second part of this is actually developing payloads based on some sort of standardized procedure, some sort of structure. And so for this, we're using NASA Systems Engineering Handbook and sort of adapting that to what we're doing. And a lot of the graduate students right now are working on developing kind of our own systems engineering handbook. that the undergraduates can use for these specific payloads. The third thing we're doing is providing educational infrastructure and kind of a learning community for students. So this is done through things like SEDS. This is done through the Space Institute, which is a new institute that's sort of tying all of space-related activities together. And it's also done through stuff like Blue 495, which was a senior class this year that was sort of a test environment to see if we could have a Blue payload developed in a full year course. So now we're going to switch gears a little bit. We're going to talk about our two current payloads, BX2 and BX3. Just for background, BX2 is about manipulating bubbles in water, basically. And this was run in the Blue 495 class. And then BX3 is about curing composites in microgravity. And this is done under SEDS as like more of a traditional project team. And I'll have Brandon speak to that one. So I was on the BX2 team. I'll talk a little bit about what we were doing. So the first thing was that we were basically manipulating gas bubbles inside liquid. So on the right, you can see this chamber. It's basically filled with just normal water. And then we have electrodes in there which make a bubble. And what we do is we take that bubble and we use ultrasonic transducers to manipulate, move that bubble back and forth across the chamber. And the way we do that is by changing the relative phase of these two transducers to create a standing sine wave that moves slowly back and forth. So the purpose of this is to improve the TRL of this technology. There's a lot of applications when you're storing fuel and water in space of actually either separating bubbles out of the liquid or creating, say, hydrogen, oxygen from water to use as propellant. And so we're improving the TRL of this technology so that it can be used in later missions when we're traveling further and further into outer space with humans. All right, I'm now going to let Brandon talk a little bit about his experience at Blue and the BX3 payload.
All right, hi everybody. My name is Brandon Dix. I'm a current rising senior at Michigan studying aerospace engineering and also astrophysics. So real quick, I'd just like to give a shout out to SEDS. I'd like to mention, so I was a transfer student and joining a club like SEDS early on really helped me get acclimated with projects like Blue, being that SEDS is kind of the umbrella club that gets everybody connected with technical projects. And now here I am on BX3. So the entire vision of BX3 started off by wanting to explore photopolymer composite manufacturing and see if it was a viable option while somebody is in space. So the research behind this would open up the door to future experimentation, as well as our own attempts to then apply what we learn about composite microstructures to a larger, more complex geometry, such as an actual component or tool for a flight system. So the whole idea is for an astronaut on the ISS or even a future space tourist if they're on their way to Mars, to be able to 3D print a mold for something that they suddenly need to make on the fly, and then use well-known composite techniques like curing fiberglass and epoxy to create an even stronger part that would be, you could compare it to when it was made under gravity. So with this idea in mind, we found evidence that suggests composites manufactured while in microgravity have different and oftentimes more enhanced material properties. This evidence came from a study at the University of Patras in Greece. They cured a sample under UV light in the parabolic flight during those short bursts of time in microgravity. But we saw this and we thought this is why our Blue suborbital flight platform could fit this project really well, because we have a much longer duration of time to cure our samples instead of those short increments that could, when you start and stop, they kind of introduce new variables. So after curing our sample in microgravity, we plan to replicate the exact flight conditions back down on Earth, but with gravity reintroduced into the equation to kind of compare. So this sets up two identical composite samples that we can both qualitatively and quantitatively compare their material properties. And using university resources such as the Wilson Center, the Van Vleck Lab, we'll be able to stress test these samples and compare the data basically. So what we're looking for isn't necessarily the strength itself, but any significant differences in the sample data. What we believe to happen in microgravity is an increased factor of what's called wettability in the fiber matrix during the curing reaction. So if this is in fact true, scaling up this micro phenomenon will allow us to create stronger, more efficient structures at the same mass of an identical component that was created on Earth under gravity. So our hope is that after all this, we will kind of open the doors to repairability and lessen the need to send as many pre-made components on board rockets, because those kind of have more expensive launch costs versus just the raw materials that you can kind of make whatever you need to on the fly. So during the whole design process, we also reached out to companies we thought would benefit from this type of material science research. And it turns out Lamborghini was actually really interested. It makes sense for a company based on the highest performance of its vehicles to be interested in this application, which then showed our student team that the effects of this discovery could kind of apply to all different kinds of industries. So the way we're designing this, as you can see on the right, is in the same 2U payload configuration as BX2. We found that a combination of carbon fiber and 3D printed components kind of gives the best balance between mass savings and configurability for future experiments to kind of use the same platform. The way this will work is that as soon as New Shepard tells us that we're in microgravity, New Shepard being the rocket, our microcontroller and onboard sensors will trigger high-powered UV LEDs that you can see pictured in there that will kind of rapidly cure our wet epoxy fiberglass. That's the sample is pictured in the middle of that payload. And then our sensors are there to keep track of environmental data inside the payload so that we can simulate the same exact environment with our Earth-based replica and hopefully get the results we're looking for. Real quick, I also just wanted to note the difference between BX2 and BX3, and that BX3 has no minimum requirements for new students to join. You could be a freshman. This setup kind of helped with recruiting a lot, it made everybody at Michigan have a chance to work on a space payload before they graduate, or even better, before they decide to take the 495 class their senior year.
Perfect. Very well said, Brandon. I would like to also kind of point out that fact that, BX2 and BX3 are basically two different approaches to the same problem. And the reason we're doing this is to figure out what works and what doesn't. And so, payloads like BX2 and BX3 kind of lead into the future of Blue, which is the last topic. So I'm going to divide this into two different sort of areas. The first is these mini payloads that we're working on with Blue Origin. So the goal with these is to really standardize this process, standardize both the development and the launch process, and so that we can get more students involved. As more students come in, we need to develop infrastructure to include more students. This includes stuff like getting credit and building courses. And so we're really happy to announce that we've partnered with S3FL so that next year the BX3 students will be getting MDP credit for their work. And then the last thing is actually developing purposeful curriculum for Blue. So bringing Blue projects into things like 305, Aero 405, so that like there is the Blimp course, the Aero 100 course, or the Hovercraft course, which is Aero 205, these Blue payloads can then be developed in the same sort of course setting and give students a real practical expertise into building space payloads. The other side of the future of Blue is what we call advanced development. This is basically what can we do that's bigger and better. And so the first one is something we're really happy to be working on, and Mass is up next, so I'm not going to steal their thunder, but we are developing the payload for that rocket, which they're about to talk about. And so that's going to be a really cool step up for us because it's bigger than a 2U. We have a little bit more freedom with as far as what we can do with that space and that mass. So that's one thing. The other thing we're looking at is orbital payloads on ISS. So for example, with BX3, right now we're curing photopolymer composite, but for someone like Lamborghini who wants to do carbon fiber, we'd actually need more time in microgravity. So something like the ISS where we can have a payload on station in space for 2 or 3 months would be an appropriate setting. So that's one thing we're working on. And then the last thing we're looking into and working on is CubeSats. University of Michigan has some really great teams, MXL, Mighty, that are working on CubeSats, Spurl as well. So kind of leveraging the knowledge of those people and the experience of those people and bringing that into more, more of an undergraduate setting would be really beneficial for students. And so that's kind of the other side of the future of Blue, is kind of developing these advanced payloads and seeing if we can also bring those into more and more students. So that wraps up the future of Blue. It also wraps up this presentation. I'd like to thank you guys for your attention, and I think we're ready to open up for questions. If you have any interest in Blue or any other questions, you want to email us personally, our emails are at the bottom there, and we'd be happy to answer any questions that are now out.
Alrighty, thank you. Submit any of the questions that you may have through the chat, or raise your hand and I can unmute you to ask your question personally. All right. Wait, Owen, are you able to see the chat?
Yep.
Okay,
I just saw Michael's. I appreciate the compliment, Michael. So Michael had a nice comment. If there are any questions, we can also answer those now, or we can do the breakout rooms if people would like to ask the questions in a more intimate setting as well.